Year 10 Circle Theorems, Lesson 1, the angle in a semicircle. So the first question that we're going to ask ourselves is whether we understand the meaning of the word theorem. So let's start by thinking of where we've come across the word theorem before. Now, if you have a think, the most common use of the word theorem in maths that you have come across is most likely to be Pythagoras' theorem. So what do you remember about Pythagoras' theorem? So hopefully you recall that if we have a right angled triangle, we can label the sides A, B, and then the hypotenuse, the longest side, can be labelled C. Pythagoras' theorem then tells us that A squared plus B squared is equal to C squared. So a theorem is a statement that we know to be true, which, when we're working in maths, we can use as a rule. In fact, there is a way of proving that Pythagoras' theorem is true for all right-angled triangles, and you will study that in more detail in Year 11. Now, you can think of a theorem as a rule that we can use to help us solve problems in maths. And what we're going to do over the next series of lessons is learn about 8 theorems or rules which relate to circles and angles in circles that we can use to then help us solve problems. And these are called the circle theorems. There are 8 of these, and today we're going to learn about one of them. So, we're going to have a look at the first theorem in action in a minute. So what I want you to do is imagine a circle. Now, the circle has a centre point, which is marked O, and a diameter has been drawn through the circle. And you can see the diameter running from A through to B. They're points at opposite ends of the circle on the circumference, and join them up, you create a diameter. Now, there is another point on the circle, which is point C on the circumference. Now, we've joined A to C with a chord and B to C with a chord as well, and we've created a triangle. Now, you can hopefully see a little measurement just in the top right-hand corner, which is where angle ACB has been measured, and it's 90 degrees. So that's this angle here. It's been measured to be 90 degrees. Now, in a minute, we're going to animate this, and we're going to move C to different positions around the circle. A and B will always be the diameter, and we're going to see what the size of the angle ACB is when C is moved to different positions. So here's the diameter AB, here's the point C on the circumference, and can you see the measurement of angle ACB, which is 90 degrees. Now I'm going to pick up point C and I'm going to move it to different points on the circumference, creating different triangles. But have a look at the angle. ACB is always 90 degrees. It doesn't matter where you place that point C on either side of the diameter, the angle in that semicircle at the circumference is always 90 degrees. Now I can change the position of my triangle by moving the diameter around, and you will see that angle C always remains 90 degrees. And this is the first circle theorem. We say that the angle in a semicircle is always 90 degrees. So let's just clarify once more exactly what we mean by this. So if we have a diameter which splits a circle into 2 halves, into 2 semicircles, we can then create a triangle by choosing a point on the circumference and joining that point, C, to the 2 endpoints of the diameter. And we can call this a triangle in a semicircle. Now, what the circle theorem tells us is that the angle in the semicircle, which is this angle here, is always equal to 90 degrees. Now, it's really important that we understand what this rule is, what this theorem actually tells us, and it's important that we memorise the wording of it as well. So in a minute, a slide is going to come up, and you need to copy down the information on this slide into your notes. So please make sure you have a heading in your notes that says Circle Theorems, and you're going to write down this first theorem that we have looked at. The angle in a semicircle is 90 degrees. As part of your notes, you will need a clear sketch diagram. So please sketch this in your notes and make sure the semicircle, the diameter, the chords, and the right angle are very clear. Now I'm just going to add a little bit more on vocabulary here, because you will hear and you will read a certain word associated with circle theorems, and we want you to understand exactly what this word means. Now the word is subtended. So what does this word subtended mean? Let's give some context to this with an example. So I could say the angle at the circumference subtended by the diameter is 90 degrees. Now what does that mean, subtended by the diameter? All it means is that this angle here, this right angle, is created from or stands on this diameter. So the two chords that create this angle here come from the ends of the diameter. So you can think of that angle as being created from the two endpoints of the diameter, and that's all that subtended means. Now you don't have to use that word yourself when you're talking about circle theorems. It is perfectly acceptable for you to memorize this statement here, the angle in a semicircle is 90 degrees, but you may see the word subtended in a textbook, and it's important that you understand what it actually means. Now, it is crucial that you memorize the wording here. The angle in a semicircle is 90 degrees. If you are asked to write down any of the circle theorems in words, you must do this using the correct vocabulary, which means you must memorize this statement and be able to link it to this diagram. Please make sure you have made a clear note of the wording of the statement and drawn a sketch to illustrate the theorem in your notes. Now in a minute we're going to have a look at some worked examples which will show you how we actually apply this theorem when we're solving problems. Now you will have been sent a PDF with the questions on that too, so you can either print that out and then work through the questions with the PDF, or you can sketch the diagrams in your notes and work through the questions. So let's have a look at the first question. Now, can you see the diameter here? And can you see a chord here and a chord here, which join up to create a triangle in a semicircle? Now, what of course we know is that the angle in a semicircle is 90 degrees. So we know that x plus 65 plus 90 must equal 180. So from there, we can very simply work out the missing angle x, which of course comes to 25 degrees. Let's look at the second example. This time, can you identify the diameter? Can you identify the triangle in the semicircle? Can you identify the angle that is 90 degrees? So here's the diameter. Here's a chord, and here is the right angle. Now, we know the angles in a triangle add up to 180, so if this one is 90 degrees, then this one here and this one here must add up to 90 degrees. So I'll simplify the working by saying x plus 34 is equal to 90, which tells me that x has got to equal 56 degrees. Now, what about example C? Can you try this one by yourself? Pause the video, have a go, come back to the video to check your answer. So here's the diameter, here's the 90-degree angle. So we know that these two must add up to 90 degrees as well, so that the angles all together add up to 180. So x is therefore equal to 18 degrees. Now, part D, let's have a go at that. So here's your diameter, and here is your triangle in the semicircle. So here's your angle in a semicircle, which is 90. Now from this one, I think we can probably straight away see that x just has to equal 40 degrees. So all three add up to 90. Part E, a little bit more interesting. Now, spot your diameter and then make sure you can see where your right angle is. It's up here. Now, there's a little bit more information in this question because they've given us this side and this side as being the same, which means this is also an isosceles triangle, which means this angle here is also x. Now, if this angle is 90 degrees, that means the other two angles, x and x, must also add up to make 90 degrees. So 2x must equal 90, which means x has got to equal 45 degrees. Now, example F, we've got two triangles within semicircles within this circle. So here's the diameter. Now there's an angle of 90 degrees up at the top here and an angle of 90 degrees at the bottom here. So we know that x plus 28 has got to equal 90 to make 180 in the top triangle. So x is therefore equal to 62 degrees. And then we know that y plus 44 must also equal 90 degrees. So that gives us y equals 46 degrees. Now, when you practice some questions on this a little bit later on, you'll be building up to more complex problems as you work through the questions. So have a look at R. Now, it might look a bit bewildering to start off with because there's so many different letters labelled on here. Now, here's the diameter running through the centre of the circle, and then we've got our triangle inside a semicircle, which means that this angle here is our 90-degree angle. So we know that 21 plus e must equal 90 degrees. Using the circle theorem, the angle in a semicircle is 90 degrees. So from here, you can very simply work out what e is. It's 69 degrees. Now, how do you then go about finding the other angles? Well, it involves more than just this circle theorem. Have a look at this line here. It's a radius, and this line here is also a radius. So these lines are equal. So if I put in some labels here, I'll call this P and I'll call this PQ, then I can say that triangle OPQ is isosceles. So that means that angle A must also equal 21 degrees. Very simply, base angles in an isosceles triangle are equal. Now I can then work out angle B using angles in a triangle. So angle B will equal 180, take away 21 multiplied by 2 because angles in a triangle add up to 180 degrees. So B is equal to 138 degrees. Now, I can then work out angle C because if you look at that, C and B sit on a straight line together. So angle C is equal to 180 minus angle B. Angles on a straight line must add up to 180. So that's 180 minus 138, and that comes to an answer of 42 degrees. Now, to finish off, there are multiple ways in which we could work out angle D. We know angle C and we know angle E, so it would be quite easy to do a calculation. But this is a radius, and this is a radius. So we know that triangle, and I'll put a point here, we'll call it R, ORQ is an isosceles triangle. And that tells us that angle D has got to equal angle E, which means it's got to equal 69 degrees. Now, just as an interesting check, let's see if C plus D plus E add up to 180. So that's 42 plus 69 plus 69, and that comes to a total of 180, so I know I've done this correctly. So quite often, problems involving circle theorems and angles inside triangles in circles will involve a multi-step process where you need to think really logically through how you're going to solve the problem. Now, that's not the only way to do question R. That could have been solved in multiple different ways with different starting points, but that is a way in which we can work through it. Now, let's look at the last two questions over here, which involve a little bit of algebra. So, here's the diameter. Here's your angle in your semicircle, which is 90 degrees. So that means these other two angles must also add up to make 90 degrees. So x plus 15 plus x plus 5 must equal 90 together. So collect your like terms. 2x plus 20 equals 90. 2x is equal to 70. And x is equal to 35. Now, if we then have to work out the actual sizes of these angles, well, this one is x plus 15, so 35 plus 15 gives me 50 degrees. And this one is x plus 5, so that is 40 degrees. Now, the very last example, here's my diameter. Here is a chord and my other chord. So here's my 90 degree angle. So again, x plus 32 plus 3x minus 6 has got to equal 90 degrees. So adding these together gives us a total of 4x minus 26 equals 90. 4x then equals 116 and x equals 29 degrees. Again, we might need to actually work out the sizes of these angles by substituting x back in. So 29 plus 32 gives us an angle of 61 degrees over here, and over here we get an angle of 81 degrees.